Good afternoon. To examine the challenges associated with low concentration measurements, we would like to start by asking a fundamental question. How does one measure quality? Is it by following the method to the letter and doing nothing to address analytical difficulties? Is it by meeting non-performance-based criteria? Or is it when the stakeholders work together and when the plant manager knows that there is a 5% chance that the true value is above the limit, or even if the lab contributed to the results being above the limit? Whenever a testing project is conducted, the attention is typically directed to the end of the process. Issues showing up at the very end of the measurement process becomes a crisis, forcing a return to earlier phases and resulting in waste of time and money, not mentioning the reduced confidence in the abilities of the people doing the work. Under a fitness for purpose orientation, the final product quality and data effectiveness depend on the attention paid at the beginning of the process, where the leverage resides, that is, where the ability to influence the outcome resides. In the minute that follow, we will briefly examine the process, the technology, the challenges, and then we'll move on to the components of our answer to the fundamental question by introducing the Bill of Rights, say a few words about detection limits, and then illustrate how to specifically answer the fundamental question. Planning means beginning with the end in mind. It is to make clear what is exactly the purpose of the test and where you want to be relatively to that purpose. Following the sampling event, the samples are delivered to the lab. Inside the lab black box, there are several complex steps that are interconnected and interdependent. In the lab, Jerry Hart and myself started at the end of the last millennium. We introduced a powerful lab self-diagnostic procedure called Performance-Based Criteria Analysis, or PBCA, which is the tool used to answer the fundamental question. Finally, the validation phase checks the ending against the beginning, and using the PBCA, one can explore the short and long-term implications associated with the test results. The technology in use is based on isotope dilution mass spectrometry. When examining challenges at low levels, one cannot get away from considering the detection limits. The facts about detection limits are that we reach a point where they are optimized, and there is little room for lowering them further unless the manufacturers develop better systems. Thus, to answer the fundamental question, we will have to consider other aspects. Let's look at the various challenges associated with low concentration measurements for dioxins when, for instance, establishing and demonstrating compliance with the MACT floor. When faced with challenges, there are essentially two paths to follow. The reactive path is driven by the question how to get rid of the problem. Unfortunately, the temptation to resolve the issue is to go for a quick fix. For example, in the case of the US EPA, the agency declared the methods, PBMS, without any adaptation of their infrastructure. This approach may solve the problems in the short term, but they will resurface later, creating a recurring pattern. The other path adopts a creative or generative orientation, which is generating a new path from where we are to where we want to be. And to effectively resolve the issue, the fundamental solution examines the problems at a deeper level. Thus, we must find out where we are and compare it to our goal or vision or to the result we want to create. To truly deal with the challenges associated with low concentrations, our vision calls for flexible tools that can adapt to changing circumstances. Therefore, we must be able to innovate and be accountable for the decision we make in the process. It's like going fishing. One needs to know what kind of fish one wants because different tools are needed for trout versus bass fishing. Before asking how, one must ask what. And the accountability is what happens when you return home with nothing to show for dinner. The what we have are forces that want to maintain the status quo. They are driven by unquestioned assumptions and beliefs about the effectiveness and relevance of existing quality control concepts, obsolete views on how things work, and the fear of complexity and chaos associated with the freedom to enhance the methods under PBMS. The gap between what we have and what we want creates a tension which seeks resolution. PBCA is the product of resolving the tension. Other factors include the regulatee, who is responsible for the selection of the appropriate method for effective decisions. The plant processes is also a factor regarding the samplings. In today's context, we will consider only the sample volume. And finally, from the lab perspective, one major contribution to addressing the challenges at low concentration can be condensed into comprehensively measuring the uncertainty in almost real time for each sample and each target analyte where and when needed. Unfortunately, measurement of the uncertainty is often ignored as one of the challenging factors. One of the key elements of our approach is the introduction of the Bill of Rights. Three basic questions are considered at the onset of any job. First, the lab performance specification, LPS, is typically set at the lab LOD. Second, the client specified limit, CSL, usually an action level, is set by the client, who also specifies the acceptable uncertainty to make an effective decision. Together, these three parameters, LPS, CSL, and CSU, define fit-for-purpose quality. Briefly on the detection limits, we first have the US EPA infamous MDL, or method detection limit, which we characterize as irrelevant for the technology under consideration. Then we have several methods that describe how to measure the EDL, estimated detection limit, in a sample and analyte specific manner. The EDL captures many relevant performance indicators. Finally, using the American Chemical Society guidelines, our lab used thousands of EDL results obtained on real samples and blank to compute the LOD. This is the LOD used in the Bill of Rights, and both the EDL and the LOD play a crucial role in the sample and analyte specific uncertainties. The procedures for measuring the uncertainty consist of the usual definition of the measurement, establishing the source of errors, and developing an equation. Then for each sample and blank, and for each target analyte and the TQ, The combined standard uncertainties are determined and plotted versus the TEQ as illustrated here for over 1,000 stack samples during a portion of the year 2012. From the data, we can derive an equation which then can be used for forecasting purposes. This chart zooms over a shorter TEQ domain. One important observation is the fact that for a given TEQ, we expect to see a distribution of uncertainties because of the various factors affecting the TEQ. The blue line represents the predicted value, and the red and green curves are the upper and lower predicted values. Using the prediction curves, we can now plan on how to best answer the Bill of Rights questions regarding the uncertainty. For example, let's assume that the plant operator wants to achieve an uncertainty of less than 10% at the 2.5 picogram TEQ per dry standard cubic meter level. The calculator tells us that at the conventional 3 cubic meter sampling volume, we won't be able to meet the CSU. In fact, the flue gas volume should be 300 cubic meter, which is pretty much what one can achieve using a continuous sampling system for a period of about 2 weeks. Should the owner-operator be interested in an action level of 32 picogram TEQ per dry standard cubic meter, then a volume 10 times the conventional volume is necessary to achieve the requested CSU. In the US, any result below the regulatory limit is considered compliant, whereas once above the limit, the facility is considered non-compliant. When the error bars are taken into consideration, the situations where the emissions are close to the limit, then the plant is possibly or probably non-compliant. From the US EPA point of view, it doesn't matter whether there is a possibility or a probability of non-compliance. You are compliant or not. But we believe the user, and in this case the regulatee, has the right to expect fit-for-purpose data. The sample TEQ can either be above or below the CSL. Of course, it's helpful to know if the lab performance significantly affects the results. In this respect, PBCA can help. PBCA is a laboratory performance self-diagnostic tool. There is no need to look at the details here. Just know that the lab report routinely contains all that information. And when the final report is issued and submitted, the lab already knows its level of performance and whether the data are fit for purpose or not. Using an emission result and the uncertainty associated with it, we can tell the likelihood that the lab performance caused the result to be over the limit. Or, if the result is below the limit, we can tell the likelihood that the result is over, but appears to be below due to random variation in the measurement process. So how do we do this? The approach is rather simple. We treat the result as an estimate of the mean of a normal distribution, and the uncertainty as the standard deviation. Then using statistical functions, we can determine the relevant probabilities. Let's consider a couple of scenarios. In the first scenario, we examine the probability that the lab caused the result to be over the limit. So the CSL is set at 200 picogram TEQ per dry standard cubic meter. The user requests an uncertainty of 20%. The result of the test comes above the CSL. And by treating the data as indicated previously, we determine that the probability the lag caused the result to be over the limit in this example is 18%, as illustrated by the shaded area under the distribution curve. Now, if we lower the uncertainty from 20 down to 10, then the probability drops from 18 to 3%, 6 times lower for a reduction of the uncertainty by a factor of 2. With scenario 2, we examine the probability that the measurement falsely lies below the limit. We keep the same CSL and initially 20% for the uncertainty. However, the result is now below the limit, and applying the same treatment leads to a probability of 14% that the true value is above the limit. Here again, if we lower the uncertainty from 20 to 10%, the true value has now a probability of being over the limit of 2%, a drop by a factor of 7. Therefore, measurement of the uncertainty matters. And I thank you for your attention.
Thank you very much. Well, thank you very much, Yves. It's good to hear something about the sort of philosophical approach to uncertainty there. I was just wondering if limit of detection and limit of quantification are treated in the same way in the States as they are in Europe. Are they defined in the same way? And you sort of implied you're not allowed to take them into account. Is that true? Do you have any comments on that?
Yes, I have a lot of comments on that. First, the LOD or LOQ, the one that my lab is measuring on an annual basis, is following basically the American Chemical Society guidelines, which was published in Analytical Chemistry in the early 80s, I think. Now, in the US, we, like I indicated, we seem to be relying on something called the MDL, the method detection limit, which has actually nothing to do, has no relation to actual detection limit on that particular compound in that particular sample. So that's why I qualify it as irrelevant for the technology in use, which is isotope dilution mass spectrometry. So as far as reporting results, you report the results based on what the method tells you to do. And there is no information about LOD, LOQ, except by method 23, you are reporting the estimated detection limit, the EDL, which is something you measure from the sample that you analyze under the condition of the analysis, of course, for each compound and for the TEQ, obviously. And this is an equation that contains many factors, including the noise, the area of the label standard that you spike in the sample before the analysis. You have the response factor used from the calibration. And of course, you have the volume of the sample included in there. So many of those factors are actually affecting the measurement of the EDL, which is what you report. Now, when you calculate a TEQ, how do you handle the non-detect? The non-detect under isotope dilution mass spectrometry, you always report a detection limit, which is the EDL, the estimated detection limit. All right, so when you calculate your TEQ, you have the option of going with a ND equals 0, an ND equals half the detection limit, or you can use the detection limit in the computation of your TEQ. On that aspect, the tendency is to adopt 1/2 the detection limit during the computation of the TEQ. If you are interested in risk assessment and looking at a worst case scenario, then you would use the full detection limit in the computation of your TEQ. So these are things that are still pretty much fuzzy and not very well defined in the US. So that's why my lab in particular, we report to our clients all the possible options so that the client decides what result they want to use in their final report to the agency.
I think that's really interesting because I would say it's a similar situation in Europe, to be honest. We seem to have endless debates about how to calculate these things and whether to take them into account or not. But of course, we're allowed to take the measurement uncertainty into account at the end of the day for compliance. And it sounds like you're not, which is a big difference. Yeah.
But I understand the position of the EPA. They say that the reason they don't consider the uncertainty in the analysis and everything is because the standard, or if you want, the statute limit, are or have the uncertainty embedded in there. Okay, so the EPA can have that opinion. I respect it. What I'm saying is that the user, the one that owns and operates a stack, a facility, they need to look for the uncertainty so that they can put their result into a context that allow them to determine whether they are in good shape, or there's a possibility that they are not in good shape, or there's a probability that they are not in good shape, so that they can foresee. But the problem is there's always a question of liability, because if you have a result that is considered compliant with no error bar, and then now you have the error bar, and it suggests that there's a probability that you may be out of compliance, then there is a risk of being considered out of compliance, which entails penalties, possibly retroactively. So what we need to do is modify the rules and regulations in such a way that we don't play this, catch you kind of a scenario. So that's why it's important to look at the belief, the mental models that we have, because some of the structures of the rules and regulations discourage people from actually doing the right thing.
Yeah. What are the sort of lowest dioxin limits that you've got in the States?
Well, like I show there, every year we have thousands of method 23, and the data is representing anything like municipal waste combustors, medical waste incinerators, cement kiln, secondary aluminum, copper smelter, and you go on and on and on. In terms of regulatory limits, it's all varying from one group to another. The municipal waste combustors, who are the oldest regulated facilities, those are regulated under a total mass balance. That is, we're looking at the sum of all the dioxins from tetra through octa. And they start moving in the TQ, because when the MWCs were first regulated, TQ concept did not exist. All the other cement kiln, for instance, and secondary aluminum are regulated on a TQ basis. And it varies from category to category. In general, it's going to be around 0.2 nanogram or 200 picogram TQ per dry standard cubic meter. Now, the TQ can be calculated using the international toxic factors or the WHO, 2008, 1998, 2005, whatever. That's something that can vary from one regulation to another. And specifically in terms of example of EDL for the TQ that we can achieve analytically speaking, we got less than 3, the EDL, that's estimated detection limit per sample. We are below 3 picogram, which is 0.003 nanogram TQ per dry standard cubic meter. And the LOD is around 5.5 to 6.5 picogram TQ per dry standard cubic meter. The LOQ varies from 13 to 16.
Okay, very good. Thank you for that information. There is a question from Mark Coleman here in the chat. He says, thanks, Yves. Just a comment, across Europe, how the uncertainty is used varies. We don't have consistency across national regulators in terms of how the uncertainty of a measured emission should be taken into account. So I think that's a comment that, we do have variability across European member states as well.
I want to point out that my uncertainty is related to the analytical aspect.
Yeah.
In the States, when you go through a compliance test, there will be 3 samples taken plus a field blank. So, from the sampling, you can determine a standard deviation from those 3 individual measurements. But that's not really an uncertainty as the way I'm defining it. My approach is a formula that is CA long.
Yeah, and it would include any process variation within that as well.
Yeah. Whereas a lot of places will use a budgeted uncertainty, so they'll define at 20%, and that's it, without actually demonstrating that. And it's 20% applied no matter what concentration you are measuring, which is totally unacceptable in my view. That uncertainty needs to be measured exactly where you needed it to be measured.
Yeah. Thank you very much for that.
It can be done.
Yeah.
By the way, the people within the EURL, European Reference Laboratory, and the National Reference Laboratory, they published, and I was part of the group involved, a procedure for measuring the uncertainty. So the EURL and NRL has publication probably going back to 2013, 14, somewhere around there, that you can access and give you an idea about how to measure the uncertainty. My approach is a whole lot more involved than the one that is described in that document, but every country is doing it its own way, as long as it's done, at least.
Yeah. Thank you. Thanks a lot for preparing the presentation and for being here in person today. It's much appreciated.
My pleasure. Thank you.
I think that sort of brings us to the end of our session now. Andy, I don't know if you want to comment on what comes next in terms of timing today. Is this the last one?
Yes, that's it from the conference sessions. I believe there is some sponsored talks straight afterwards. But as of the conference, yes.
Great. So thank you all for attending, and again, apologies for the various difficulties, but hopefully you've managed to find the bits and pieces you wanted to listen to. And thanks to all the presenters again for their contributions. It's been very good. And bye for now. Bye until next time. In person.
Yes.